You should have that formal definition for the derivative of a function up at the top of your notes paper. Notice that it's a definition defined by a limit. And even though we dabbled with it in the last chapter, there was the end of the previous video where we found our first actual real derivative function using that definition. It is true that moving forward, we have discovered easier ways to find the derivatives of pretty much all functions. But your ability to trace those derivatives back to this formal definition, which requires a limiting process, is going to be critical to your success. So we are going to practice using this process as a sort of an earning of the right to use the shortcuts later. So stick with me, practice this. Remember your algebra rules that we talked about in section 2.1 for simplifying limits, where we end up with a 0 over 0 problem. So this is the next one we want to try. Can you use the definition of the derivative to find f prime when f is 1 over x? Let's see if I can cover this up so it's not too... So we don't have any spoilers. There's a spoiler down at the bottom. Okay, so I'm going to use the marker to kind of follow along here. So there's my limit definition. The limit as h approaches 0 of f of x plus h minus f of x all over h. Do you need to know that? You need to know it by heart. You need to know it by double heart. Like, get it tattooed on your body if it comes down to it that well. So we practiced this a little bit back in, I think it was 2.4. If f of x is 1 over x, then what is f of x plus h? It means make x plus h the denominator. So this is f of x plus h minus f of x all over h. I'm going to take the limit as h goes to 0. Well, we probably recognize this. We had tried problems like this back in 2.1. I'm going to try to get one fraction in the numerator and one fraction in the denominator so that I can change to multiplying by the reciprocal. So I notice that the missing factor in my first fraction is x, so I'm going to multiply top and bottom by x. The missing factor for my common denominator in the second fraction is x plus h, so I'm going to multiply by x plus h over x plus h. And once I've done that, I have the same denominator, and as long as I remember to distribute the subtraction, I'm going to have to subtract x and then subtract h. Then my new function, my new limit problem, is the limit as as h goes towards 0, of x minus h. So the x's cancel out, and I'm ending up with a negative h in the numerator. Brings me up here. I'm going to move me over here. And I have the limit as h goes to 0 of negative h over x times x plus h all over h. I'm going to change to multiplying by the reciprocal. I notice now that my h's will cancel but leave behind a negative 1. And I end up with the limit as h goes to 0 of negative 1 over x times the quantity x plus h. Now, I won't have a problem when I substitute 0 in for h. I'm going to have x times x in the denominator, and that's what happens. I end up with a derivative rule of negative 1 over x squared. And it turns out that that's exactly correct. If you needed to find the slope of the 1 over x function, then you could use this formula, negative 1 over x squared, to give you the slope at any point on the original f function. If you think about that process we used, thinking of 2 points on a curve and finding the slope of the secant line and then letting the 2 points get closer and closer together. If you kind of think about it in a different way, you would come up with this definition, this formal definition for the limit. Your book calls this the alternative form, but it's just as important. It shows up just as much on the AP test. So there's a place for this at the bottom of that first page. F prime of a, so the derivative of f at a specific x value, which we're going to call a, is the limit as x approaches a of f of x minus f of a over x minus a. There's a place for the formal definition of the derivative on your important facts paper. It'd probably be a good idea to put both of these in. I've never had another class put both of them in. Let's put both of them on your important facts paper. All right, so I'm going to use that new alternative form of the derivative to find the derivative of x cubed. Pay close attention because I'm going to leave letter B as an exercise for you. So I'm going to take the derivative of f at a is the limit as x goes to a of f of x plus h minus, nope, I got all excited about the old version, f of x minus f of a over x minus a. So in this case, that's going to be the limit as x goes to a of x cubed minus a cubed all over x minus a. Oh, it's kind of like nicer without that little plus h messing up what my functioning looks like, what my f of x rule does to the input. So now I have to think about this. I certainly can't replace x with a because I'm going to have a 0 over 0 problem. So I'm going to need to think of something, and it turns out that x cubed minus a cubed factors. This is the difference of cubes pattern that you learned in Algebra 2. So I'm going to factor that numerator. X cubed minus a cubed factors as x minus a times the quantity x squared plus ax plus a squared. I'm going to move me out of the way and come up to the top of that next column there. So that's great news because watch what happens, right? My x minus a factors cancel. That's the second time this year that a sum or difference of cubes pattern has come up. It's good to remember. So if you didn't remember it, you might do a little practice on it. So I'm going to take the limit now as x goes to a of x squared plus ax plus a squared. Now I don't have any division possibility anymore. I'm going to replace x with a. I'm going to get the limit as x go. No, it's not even limit anymore. I'm just going to replace it. That's going to be a squared plus a times a plus a squared, which is going to be 3a squared. So the derivative of x cubed at the place where x equals a is 3a squared. Final answer. So I said I'm going to leave letter B as an exercise for you. Maybe you want a hint. So you're going to use that algebra technique for simplifying limits, the one that hasn't shown up in this video yet. You'll do great. All right, so let me drive home a point in case I haven't driven it home strong enough yet. A derivative is a function that tells us the slope anywhere of some original function. So the derivative is a new function that's related to like a beginning function and tells us the slope of that function anywhere that we might care to know. So that makes it, in some cases, easy to find the derivative because we can think about the slopes of functions we already understand. Now, the only slopes we really already understand are the slopes of linear functions. So we're going to take everything we know about finding the slope of a line. We're going to combine it with what we know about derivatives, which is the definition comes from a limit, and a limit only exists if the limit only exists at some x value if the limit from both directions is equal. So think about what that means. A derivative is only going to exist at a place on a function where the slope from both sides, the derivative from both sides, is equal. So I'm going to leave this problem for you to practice. I'm going to do a similar problem here. So check this out. I have a function, f of x. It's piecewise and it's linear. It's made up of 1, 2, 3, 4 line segments, essentially, right? So, can I make a graph of the derivative? Well, since the function f of x is piecewise, the derivative we can also think of as piecewise. So I'm going to march piece by piece along this function and find the derivative and use that to find like the altogether derivative of the function, which I'm going to graph down below. Oops. Let's do this. There we go. Okay, so check out this piece. Between 0 and 1, that it's linear, f is linear, so I can figure out the slope. It looks like this little line segment contains 1, 2 and 0, 0, so the slope is 2. The slope is 2 along that whole chunk of this graph. So watch me graph the derivative. The derivative is a constant, 2. Between 1 and 3, between 1 and 4, I have another linear chunk, but the slope is different this time. This time I have a rise of 1 over a run of 3. So slope 1 over 3. Watch me graph that. Between 1 and 4, the slope of f is a constant 1/3. So now let's talk about what happens at 1. I can't fill in either dot on my derivative function at x equals 1 because the derivative of f does not exist at x equals 1. A derivative is a limit, and a limit only exists if the limit from the left is equal to the limit from the right. So the slope as I was coming toward 1 from the left was 2. The slope as I was coming toward 1 from the right was 1/3. The slope is not the same from both sides. The derivative is not the same from both sides. So I cannot say what the derivative is. So notice that both of these circles got left blank. Between 4 and 6, that's a slope of 0. So you can see that I've graphed a line segment here at x equal with a output, a y of 0. And then here, I finally have a negative slope. That looks like a fall of 3 and a run of 3, so slope -1. You can see here. Notice at x equals 9 and also at x equals 0, I have colored in that point on my derivative. Since my original function f is not defined to the right of 9, I don't have to worry about finding the slope from the right as I come toward 9, the derivative as I come toward 9 from the right. Because it doesn't even make sense to talk about that in this context where the domain of the function is simply 0 to 9. Nothing to the right of 9, nothing to the left of 0. So there's a really similar problem on your notes paper. That's going to be your job to tackle next.